please.
Okay, great. So thanks a lot for this opportunity to present my work. The work I'll be discussing today was completed in collaboration with Antal Levitsky from Brown University and with Minkyu Kim from Sogang University and Jaco van Zyl from the University of Cape Town. So I'll be talking about the space of gauge invariant operators at finite n. Why would I be interested in that? Well, first of all, I'm going to argue that this is related to studying the Hilbert space of gravity at finite n, the gravity Hilbert space of the dual to the CFT. And we know that the gravitational coupling becomes 1 over n squared. So we're studying properties of the Hilbert space of quantum gravity at strong gravity. We're looking at some strong gravity effects. Okay. So first of all, we know by holography that every state in the gravity is dual to some state in the CFT. And if we use the state operator map in the CFT, each state in the CFT is dual to some operator. And one of the first checks that was done is the spectrum of single trace chiral primary operators was compared to the spectrum of supergravity modes. And there was a complete match between the two. More than that, if you work in the n tends to infinity limit with fixed Toft coupling, then you find that the single trace operators diagonalize the two-point function, as I've shown in the middle equation in my slide. And then, in addition, sorry, let me just hide this. In addition, if we calculate some correlator of some product of single trace operators, you land up doing sums over pairs of operators, just like a Wick contraction. So in this way, you're able to argue very convincingly for an identification of Kaluza-Klein graviton creation operators with single trace operators in the CFT. And in this way, we see the Fock space of supergravity emerge from the CFT. At infinite n, these Fock space states are orthogonal. But at finite n, there's 1 over, well, when you include 1 over n effects, there are gravitational couplings so that these Fock space states start to mix, and it matches exactly with the mixing that you see from the gravity picture. If you really take n to be finite, you can study operators that have n fields in the operator. These have been argued to be dual to giant graviton branes, so some sort of a soliton in the dual gravity theory. And at finite n, we can also consider operators which have a dimension of order n squared. They're built from using n squared fields. So in this situation, Lin, Lunin, and Maltasena have studied the duals to these operators in a lot of detail, and they're actually represented by new geometries. So the point is, amongst these gauge invariant operators in the CFT, you find multi-gravitons, gravitons, solitons of the dual gravity, and new space-time geometries. So the point is that the space of gauge invariant operators in the gauge theory reproduces the Hilbert space of the dual holographic gravity theory. And in this talk, I'm trying to describe the structure of the space of gauge invariant operators. Now, I'm immediately going to specialize to quantum mechanics where things are much simpler. There are many limits you can take of n is equal to 4, for example, where you get a quantum mechanical system. You can look at near BPS limits where you take an S wave reduction on the S3. You could look at things like the BMN matrix model, different limits of spin matrix theory. So these matrix quantum mechanics are catching specific sectors of the original ADS5 cross S5 duality with n is equal to 4 super-Young-Mills. So let's start off just with a single matrix where everything is very well understood. So we've got a single matrix, we've got a UN gauge symmetry, X transforms in the adjoint of the gauge group, and then what is the space of gauge invariant operators? Well, it's freely generated by these phi k's, which are just trace of X to the power of k. When I say freely generated, I mean the phi k's don't obey any relations. So you can't relate phi k with one value of k to phi k with another value of k. They're really all independent. And when I say the space of gauge invariant operators is generated by them, I mean that the complete space of gauge invariant operators is given by polynomials in the phi k. Things change when you get to finite n. And the reason for that is that there are trace relations. So here's an example of a trace relation at n is equal to 2. Any 2 by 2 matrix obeys this equation that I've written in red. And if I translate that into the phi's, it tells me now there's an equation relating phi 3 to phi 2 and phi 1. So the generators are no longer free. They satisfy some relations between each other. So the question you can ask is, how does this modify the space of gauge invariant operators? Now, in the case of a one matrix model, we know the answer very well. There's a truncation to the generators. We take phi k to be trace x to the k, and we let k run from 1 up to capital N. These are again all free, and they again generate the complete loop space, the complete space of gauge invariant operators. So for the case of a one matrix model, we know very easily how to work at finite N. But I'm interested really in the case of D matrices, so a D matrix model. So now I'm going to consider matrices XA, where A goes from 1 to D. There's still a UN gauge symmetry, and the XA still transform in the adjoint of the gauge group. At n is equal to infinity, the space of gauge invariant operators is again freely generated. In this case, my generators are the set of independent single trace words. And the question I want to answer is, how is this description modified at finite n? And the way that I'm going to answer this question, what do we need to do to answer it? We need to solve the complete set of trace relations for multi-matrix models. So if you were to write down the complete collection of trace relations and solve them, what's the structure of the space of gauge invariant operators that you get? Here's an outline of my talk. So I'm going to need some invariant theory. I think that maybe this is not a very familiar tool in physics. So I'm going to introduce all of the invariant theory that I need by doing some counting. And after I finish the counting, you'll know exactly what results I'm using, and you'll have some intuition for them. Then I'm going to give you a statement of the result that we found. And then to convince you that this result is correct, I'm going to give you a careful problem statement that I'll solve in the case of one matrix. And then with the help of the Moline-Weil formula, I'll solve it for 2 and 3 matrices. And once you've got the idea of what we're doing, I'm then going to show you some general lessons that we've learned. Okay, so let's start with a counting problem. So I just want to know how many polynomials I can construct of degree d using x and y. And to give an example, at degree 2, I could have x squared, xy, and y squared. So there's 3 degree 2 polynomials. It's that 3 that I'm interested in. That's the counting that I'm after, getting hold of that 3. So how do I do this counting? Well, there's a nice trick. Let me take 1 over 1 minus x times 1 over 1 minus y. Each of these factors can be expanded as an infinite series, and then I can multiply the 2 brackets. What you see in the last line is what I've got listed here is every polynomial I was writing in the list above, and each appears with coefficient 1. So if I now set x is equal to t is equal to y, then for example, my t squared, xy, and y squared becomes 3t squared. And this is 3 degree 2 polynomials. This function, 1 over 1 minus t squared, is called a Hilbert series. And expanding it in a power series, the coefficient of t to the n, Cn, tells me how many degree n polynomials I can construct from x and y. And from this derivation, you can see that there's 2 factors sitting in the denominator, 1 minus t times 1 minus t. 1 comes from the x and 1 comes from the y. So for each of our generators of this ring, we've got a factor in the denominator of the Hilbert series. This is a very general rule. If I now wanted to construct degree d polynomials using these 4 generators, 2 of degree 1, x1 and x2, 1 of degree 2, x3 squared, 1 of degree 4, x4 cubed, I would get a Hilbert series that has 4 factors in the denominator. There's t cubed in one of the factor, t squared in one of the factors, matching the degree 2 and degree 3, and 2 of the factors are just linear in t, matching the degree 1 generators. Now I've told you that these Hilbert series are counting the polynomials which are freely generated. What does freely generated mean? It means these generators, the x1, x2, and so on, do not obey any relation. This is unusual. Most counting problems have relations between the generators, and free counting problems are the simplest kind of counting problems you can consider. To see something a little bit more representative, imagine we count spherical harmonics in d dimensions. Well, angular momentum n will correspond to a degree n polynomial. I've got d generators, each of degree 1. So your first guess for the Hilbert series might just be 1 over 1 minus t to the d. We've got d generators of degree 1, so that makes sense. Actually, that's wrong. And the reason why it's wrong, if I look at angular momentum 0 spherical harmonics, well, 1 is angular momentum 0, but so is the sum of the squares. So I shouldn't count these two as distinct. Even worse, any polynomial multiplied by 1 should not be counted as distinct from the same polynomial multiplied by the sum of the squares. So I've overcounted because I counted each of these separately. To correct for that, I need to subtract something off, and that's the minus sign sitting in the numerator. I've got a minus t squared because my constraint is degree 2, and this minus sign is correcting the overcount. There's a lot more things that we could say, but the only thing I want you to notice is whenever we have got constraints in the theory, we overcount. So we need to subtract something in the numerator to correct for that overcounting. So if I show you a Hilbert series and none of the terms in the numerator are negative, it means that for that counting problem, all of the generators are free. For the problems that we study today, all of the generators are going to be free. So this counting problem now is the most important one, and this is the result that I'm going to be using. So we're again going to count degree d polynomial, but I'm going to change the rules a little bit. I can use x and y freely, so I can raise them to any power. And then I can use 1 of, and exactly 1 of, 1 w squared and v cubed. So what polynomials can I have? 1 times anything made out of x and y, w squared times anything made out of x and y, and v cubed times anything made out of x and y. And if you expand these out, just like we did above, you will find that we are generating every polynomial consistent with the rules that I've written down, and we're generating each polynomial exactly once. So setting all of the variables equal to t gives me the Hilbert series for this counting problem. And you can check that if you series expand this Hilbert series, again you count each polynomial of degree n. That's the coefficient Cn. This is an important result. Let me summarize it. So the Hilbert series takes this form. The polynomials that we're counting take the form of the last equation on the page. We've got x to the n, y to the m. N and m can be any non-negative integer. So x and y act freely. This x and y are encoded in the denominator of the Hilbert series. So the denominator of the Hilbert series tells us about generators that act freely. The 1 w squared and v cubed, we must use exactly one of them, and we only use it once. So those generators that act at most once are encoded in the numerator of the Hilbert series. So if I show you a Hilbert series like this, all positive coefficients in the numerator, so we don't have to correct for any overcounting, there's no relations between the generators, but we know immediately the denominator tells us about generators that act freely, and the numerator tells us about generators that act at most once when we are generating our ring. So I've just told you all about Hilbert series. What's the relevance of Hilbert series for our problem? Well, to see that, I'm going to study multi-matrix harmonic oscillators. And the partition function is the usual thing. It's a sum over all states in the theory. And for each state, what I sum is e to the minus beta times the energy of the state. And beta is the inverse temperature as usual. So how do I calculate this partition function? Well, as usual, I can use matrix creation operators to create my different eigenstates. And then each energy eigenstate corresponds to some trace of A daggers acting on the vacuum. I must take the trace because I'm looking for something that's gauge invariant, so all indices must be contracted, but it need not just be a single trace. I could have a double trace, a triple trace, any trace structure, so long as all indices are contracted. Now, the important thing here that I want you to pay attention to is that for every energy eigenstate, I have a polynomial in the A daggers. So if I'm summing over states, I'm actually summing over polynomials. The other thing to pay attention to, I'm going to subtract off the ground state energy so that the vacuum has an energy of 0. I'm going to normalize things so that a dagger adds 1 to the state. So then I should count the number of a daggers, and that gives me the energy of the state. But equivalently, the number of a daggers is the degree of the polynomial. So my partition function, which is given by a sum over states, I can think about it as a sum over polynomials. And for each term in the partition function, I add e to the minus beta times the energy. But setting x equal to e to the minus beta, I'm summing x to the power of n, the degree of the polynomial, for each polynomial. But summing over the polynomials with x to the degree of the polynomial for each polynomial is a Hilbert series. So when I calculate this partition function for the multi-matrix harmonic oscillator, I can think about it as a Hilbert series. And then I'll use the results that I just showed you about Hilbert series. Okay, so let me show you a couple of results that we get. So we'll talk about how to calculate these partition functions. But for all of the multi-matrix model harmonic oscillators that I study, the partition function is always a sum of positive terms in the numerator. So CIS are all positive integers divided by a product of factors. And thinking about this as a Hilbert series, so now we're making use of the intuition that we got from this counting problem. Each factor in the denominator is associated to a generator that acts freely. This is called the primary invariant in invariant theory. And if you've got an x to the j in your factor in the denominator, this corresponds to something that is degree j in our x's. It's always a single trace or sum of single trace terms. You can always pick it like that. How many primary invariants do we have? Well, it's equal to the number of factors that you have in the denominator of your partition function. Each monomial in the numerator, xi, is associated to an operator of degree I. And in general, this operator will have some complicated multi-trace structure. And in invariant theory, this is known as a secondary invariant. How many secondary invariants are there? Well, you could evaluate the numerator at x is equal to 1, and that tells you how many secondary invariants. So there's one for each monomial appearing in the numerator. And now we have the equation at the bottom of the slide, and this is just a mathematical fact about the space of gauge invariant operators. It can be written as a direct sum. Each term in the direct sum is labeled by a specific secondary invariant, and it's dressed by a product over the primary invariants, and you're allowed to raise each primary invariant to any non-negative integer power. So that's just a mathematical fact. I'm now going to suggest a physical interpretation, and well, my physical interpretation might be wrong, so this is where you could criticize what I've done. If we look at these terms that are appearing here, the blue terms look like they're creating a Fock space. This just looks like some A daggers raised to some powers. So I'm going to want to identify the primary invariants as perturbative degrees of freedom, and they generate a Fock space structure. On the other hand, the secondary invariants only appear linearly, and there's only one in each term. So the secondary invariants look like non-perturbative states or backgrounds of the theory. Think about, say, a soliton solution in a quantum field theory, or some new gravity background in supergravity. In the case of the soliton, you can add perturbative excitations. In the case of the supergravity background, you can put gravitons on top of that background. So I want to think about the secondary invariants as non-perturbative states of the theory. And in the remainder of the talk, a lot of the talk is going to be trying to motivate why that interpretation is actually correct. Okay, so that's the result that we find. How am I going to convince you that this result is actually true? Well, this is the problem that I'm going to start off solving. I want to study the matrix quantum mechanics of d n by n Hermitian matrices. And my Hamiltonian is just going to be the usual oscillator. So trace of momentum squared plus trace of position squared, and there's one term for each matrix. I have the usual equal time commutator. The UN indices are around, so I've got a matrix momentum, a matrix X, and the chronic is on this side. Their form is completely fixed by UN invariance. The model has a UN gauge symmetry, X is in the adjoint, and pi is in the adjoint. And the question that I want to answer is, how do I write down the space of all gauge invariant operators at a given time? And this is the space of traces of arbitrary product of these x's. And this is what I call loop space. To give you a description of loop space, what would a reasonable description be? Well, I want to give you a set of generators for this loop space, and I want to tell you what is their algebraic structure. For the case of a single matrix, which is simplest, well, I solve the eigen problem of my Hamiltonian as usual with the creation operator, so just x minus I times the momentum. I've taken my Hamiltonian to be the trace of A dagger A, so that I've subtracted off the ground state energy. And I know the partition function calculated with this Hamiltonian can be interpreted as a Hilbert series. So this is the answer I get for the partition function. In a few slides' time, I will show you how we calculate such partition functions. But if you look at it and you think about this as a Hilbert series, well, you would say there's a total of n generators. And by looking at their degrees, degree 1, degree 2, degree 3, up to degree n, a natural guess for these generators would just be trace of x to the power of k, where k runs from 1 to n. The partition function suggests this answer, but it certainly doesn't prove it. So how do we prove that this is the correct interpretation of that partition function? Well, we do that by using trace relations. So let's pause to discuss where trace relations come from and how the complete set of trace relations can be derived. So if I want to work out the trace relations for 2 by 2 matrices, the generalization for arbitrary n will be trivial once we've understood 2 by 2. The trace relations have 2 plus 1 factorial, so 6 terms. And how do we get the trace relations? Well, pick up any three 2 by 2 matrices, W1, W2, W3. So these are all 2 by 2s. I've written them next to each other in this first term, W1, W2, W3. I've displayed the row and column indices for each matrix. Now what I'm going to do is I'm going to anti-symmetrize over the column indices. So the first permutation I could do is I could swap 1 and 2. And that's how I get the second term, and there's a minus sign. I could also swap 2 and 3, which gives me the third term, or I could swap 1 and 3, which gives me the fourth term. For each of these terms, I've done one swap, and that's why there's a minus sign. The last two permutations I could do, I could first swap the column indices of 1 and 2, and then swap the column indices of 2 and 3, or I could swap the column indices of 2 and 3, and then 1 and 2. And that gives me the fifth and sixth terms in this equation. They come with a plus because I've done two swaps to get those two terms. What have I done by writing this down? I've anti-symmetrized in I1, I2, and I3, which each take two values because W1, W2, and W3 are 2 by 2 matrices. Well, anti-symmetrizing three indices, which each takes two values, always gives you 0. So this equation above is equal to 0. I'm going to take I1 and I2 and I3 to be summed, so it's an equation between traces. What Procesi proved in the mid-70s is that if I construct W's from a single matrix, it gives me the complete set of trace relations for a single matrix model. If I construct W1, W2, and W3 from D matrices, and I let W1 and W2 and W3 be arbitrary words constructed from these D matrices, I get the complete set of trace relations for a D matrix model. So this gives me a complete description of the trace relations for n is equal to 2. Notice the trace relations are equally applicable for bosonic and fermionic matrices. Certainly I didn't swap the positions of any matrices. More than that, I needed no properties about the potential or the coupling strength. So the trace relations hold very generally for any potential I have in my Hamiltonian and any coupling strengths. The only parameter the trace relations care about is capital N. So once I've told you that n is 2, I know that this is the trace relation. For n by n matrices, the derivation is exactly the same. So I now consider n plus 1 n by n matrices, W1, W2 up to Wn plus 1, and I again anti-symmetrize in the column indices. Anti-symmetrizing n plus 1 indices, which each takes n values, again gives 0. Okay, so those are the trace relations, the complete set of them. This is where they come from. Let's now return to our one matrix problem, and I'm going to look at n is equal to 2 for simplicity. So here I've again written the trace relations, but in the form of actual traces. You can see there's 6 terms here, and it should be clear how I got these 6 terms. I can build W1, W2, and W3 out of my single matrix X. I'm choosing W1 to be X to the K, W2 and W3 both to be X, and then I get this equation written in red. And you can see that indeed my invariants are no longer free. These traces obey relations. If I set k is equal to 1, this 2 phi k plus 2 term becomes 2 phi cubed, and I can solve for phi 3 in terms of phi 2 and phi 1. If I set k is equal to 2, I can solve for phi 4 in terms of phi 3, phi 1, and phi 2, but I know phi 3 in terms of phi 1 and phi 2. So I can write phi 4 in terms of phi 1 and phi 2. So using this red equation, I managed to prove that I can express phi k with k greater than or equal to 3 as polynomials in phi 1 and phi 2. This proves that I only need phi 1 and phi 2 to generate the complete space of gauge invariant operators. And I can't use that equation in red to determine phi 1 and phi 2 because the trace relations only kick in when I have n plus 1, which means 3 or more matrices inside the trace. So this would be the proof that for n is equal to 2, the space of gauge invariant operators is freely generated by phi 1 and phi 2. By using the trace relations for n by n matrices, you can prove that the space of gauge invariant operators is freely generated by phi k, where k runs from 1 to n. This is going to be the structure of all of our subsequent arguments. We're going to calculate a partition function, and then using that partition function, we're going to guess a set of invariants. And based on the invariants that we've guessed using the trace relations, we'll prove that those really do span all gauge invariant operators. So the partition function that we calculated is only a Hilbert series for the harmonic oscillator, but the fact that these span the space of gauge invariant operators was proved using the trace relations, so it holds for all potentials and all coupling strengths. So we're going to get very general results. How do we calculate the partition function for multi-matrix models? Well, we use the Moline-Weil formula. So I just want to remind you of the Moline-Weil formula. So I've got my partition function, z of beta. I'm going to imagine that I am looking at the contribution from a state created using N1A1 daggers, N2A2 daggers, and NDAD daggers. So for each oscillator that I've got, I'm going to diagonalize it using creation annihilation operators, and for x1, I'll have A1 daggers and so on. Just for the clarity of this formula, let's imagine that the A1 daggers create states of energy E1, the A2 daggers create states of energy E2, and so on. And I'll imagine I've subtracted off the ground state energy. So these x's to the various powers, that's the contribution to the Boltzmann factor from the different oscillators. And then to complete the expression for the partition function, I need to multiply by the number of singlets that I can produce from N1A1 daggers, N2A2 daggers, and going up to NDAD daggers. So how do I calculate this number of singlets? Well, the simplest way to do it is to use characters. I take the character of the representation that this state belongs to. I multiply by the character of the singlet, and I integrate over the group. So what representation does this state belong to? Well, we know that A1 dagger, for example, belongs to the adjoint. If I've got a product of N1 A1 daggers, because the A1 daggers are bosons, they're symmetric when I swap them. So I get the symmetric product of N1 copies of the adjoint. For the N2 daggers, I get the symmetric product of N2 copies of the adjoint, and so on, up to the symmetric product of ND copies of the adjoint. And then to get the total representation, I just get the tensor product. So the number of singlets is exactly given by this integral over un. We know that the character of tensor products is just the product of the characters. We also know that the character of the singlet is just 1. So in the end, to get hold of my partition function, I have to calculate this integral of the unitary group. Characters only depend on the eigenvalues of the matrix U, so I can immediately integrate out all of the angles in this unitary matrix U, and I'm left with an integral over the eigenvalues of U. One of those integrals can be done immediately, so I'm left with an integral over n minus 1 eigenvalues. The eigenvalues of the unitary matrix have magnitude 1, so I'm left with n minus 1 integrals over unit circles. I've got a very explicit integrand. As soon as you tell me what d and n are, I can work out exactly what this integral is. So I can work out this partition function just by using the residue theorem. So once you've told me what d and n are, I've got a completely explicit expression to evaluate, which I just evaluate using Cauchy's residue theorem. So that's what I'm going to be doing in the rest of the talk. So if we look at a matrix model, two matrix model with n is equal to 2, I've got matrices x1 and x2, which I call x and y. And just to make things transparent, I'm going to introduce a chemical potential for x, a chemical potential for y. So my partition function will be a function of little x and little y. And my partition function takes the form that's shown over here. Thinking about it as a Hilbert series, well, this is obviously a freely generated ring. I've got a product of 5 factors in the denominator, so there are 5 generators. And because I've graded things, it's easy to guess what those generators are. I've got the trace of x, the trace of y, trace of x squared, trace of xy, trace of y squared. So these 5 generators, I expect from this partition function, will generate the complete space of gauge invariant operators. To prove that, I'm going to use the trace relations. So the trace relation says T2 of ABC is equal to 0, and T2 of ABC is this polynomial in A, B, and C. So to give you a specific trace relation, I have to tell you what A, B, and C are. So I'm going to start from these 5 invariants. I'm going to choose suitable trace relations, and I'm going to prove to you that I can construct every single gauge invariant operator in this theory. Before we get going, notice I've got all traces of a single matrix and all traces of matrices squared amongst my invariants. Okay, so now let's look at gauge invariant operators that are given by taking a trace of 3 matrices. And I'm going to imagine that n of these are x matrices and m of them are y matrices. So n plus m is equal to 3. For every choice of n plus m, I've got a unique trace relation and I've got a unique gauge invariant operator. So for example, when m is 2 and n is 1, the unique gauge invariant operator that I have is the trace of xy squared. And the trace relation that I'm going to pick, I pick a to be x, b to be y, and c to be y. That's the only choice when I've got these 3 matrices. The last term is the operator that I want to determine. The first 3 terms are traces of either 2 or 1 matrix, so they appear amongst my generating set, and I learned the trace of xy squared is this polynomial in terms of my generating invariance. Equally simple argument tells me what the trace of xy squared is, and using the single matrix trace identities, I learn what the trace of x cubed is and what the trace of y cubed is. So this gives me formulas for all traces of products of 3 matrices. There was always a unique operator and a unique trace relation. This doesn't continue. In fact, already at length 4, if I pick 2 y fields and 2 x fields, there are 2 independent operators. There's the trace of x squared y squared and the trace of xy xy. However, in this case, we find there's 2 independent trace relations. I can pick a to be y squared, b to be x, c to be x. That determines the trace of x squared y squared. The second trace relation is when I pick a to be xy, b to be x, and c to be y, and that determines the trace of xy xy. So what was important in this example is that even though we had a growth of independent operators, it was matched by the emergence of additional trace relations. So will there always be enough trace relations to determine all of the operators? That's what we have to prove. For any other value of m and n, for a trace of 4 matrices in the trace, there's always a unique operator and a unique trace relation. To prove to you that this is true for any m and n, I'm going to give a proof by induction. So this is my induction hypothesis. Single trace loops containing at most k matrices are determined by a generating set using the trace relations. So if I've got a product of k matrices, any k matrices or fewer inside the trace, they can be written as a polynomial of those 5 invariants that I had. That's my induction hypothesis. Using the hypothesis, I'm going to prove that all single trace loops containing k plus 1 matrices in the trace are determined by a generating set of trace relations. And what do? Well, as usual, I just have to show you which trace relation determines our gauge invariant operator. So let's start off with trace of x to the n1, y to the m1. And this is not the most gauge invariant operator, but it's just the one I'm going to start with. I can assume k is greater than or equal to 4. I've already proved the induction hypothesis for k is equal to 4. So k plus 1 will be greater than or equal to 5. Since n1 and m1, neither of them are negative, at least one of these integers must be bigger than 1. Let's say that n1 is bigger than 1. Then the trace relation I'm going to tell you to look at is a is x, b is x to the n minus 1, and c is y to the m1. From that trace relation, we get the equation shown below. The first term is the operator that we want to determine, and all other terms in this trace relation have k or fewer matrices in the trace. So this equation determines the trace of x to the n1, y to the m1. Now, to prove the statement in general, I need to consider the most general trace relation, the most general gauge invariant operator. And this is what it looks like. X to the n1, y to the m1, x to the n2, y to the m2, going all the way up to this teal x to the nq, y to the mq. So there's a total of q x, y blocks inside this trace. This I'm going to call a type Q invariant. On the previous slide, I had a type 1 invariant. If I look at the trace relation obtained by setting a is equal to x to the n1, b is equal to y to the m1, and c is equal to the rest of the operator, this is what the trace relation looks like. The last two terms in this trace relation have k or fewer matrices inside the trace, so the last two terms of the trace relation by the induction hypothesis can be written as polynomials in our generating invariants. The first term is the type Q invariant we want to determine. The second term, because n1 and n2 are combined and mq and m1 are combined, is a type Q minus 1 invariant. So if I can determine the type Q minus 1 invariant, I can determine the type Q invariant. But we've already determined the type 1 invariant. So because I can determine the type 1 invariant, I can determine the type 2 invariant. But then because I can determine the type 2, I can determine the type 3. So now I just do a recursion through Q, and that proves that I can write every single gauge invariant operator in this theory in terms of those 9 primary invariants. There's 2 points to be aware of. Our argument that the Hilbert series is computing a partition function holds only for the oscillator. So the only time that your partition function will be a Hilbert series is when your Hamiltonian is a harmonic oscillator. But our proof that the generating invariants span the space of gauge invariant operators used only the trace relations. And the trace relations are completely general statements, true for any interaction and coupling strengths. The only thing they depend on is the value of n. So the statement that these 5 invariants generate all possible gauge invariant operators in this 2-matrix model at n is equal to 2 is true for any potential that sits inside the Hamiltonian. Okay, so let's now do another example at n is equal to 2, and this is 3 matrices. By the way, sorry I went through these details, but there's going to be no more details like this. I just wanted you to be absolutely clear on how we are making the claims that we are claiming. So if we look at this 3-matrix model at n is equal to 2, I'm calling my 3 matrices x, y, and z. I've again introduced a chemical potential for each. That's the form of the partition function. And the thing that's interesting about this example is that here we see a non-trivial secondary invariant. So there's 9 primary invariants that we can very easily write down. And there's 2 secondary invariants. One is trivial, but the second one from the grading, I can guess, is just the trace of x times y times z. Now remember, the primary invariants I can raise to any power, but the secondary invariants appear only linearly. So what I want to learn from this example is, why do I only use the secondary invariants linearly? Why do I never square a secondary invariant? And the answer, of course, comes from the trace relations. If you use the trace relations and you do a little bit of work, you can prove the equation shown on the slide. So this is just a consequence of trace relations. What does it say? S squared plus S times some polynomial in the primary invariance plus 1 times a polynomial in the primary invariance is equal to 0. So what this tells you is S squared as an operator is not independent from operators which are linear in S and 1. So the reason why we don't include S squared is to avoid redundancy. this operator s squared is already inside our space once we've included everything linear in the secondaries and arbitrary powers in the primaries. So the reason why secondary invariants act only linearly is to avoid redundancy. The trace relations allow us to express s squared in terms of operators that we've already got. Now, in this problem, there was a single secondary invariant. But if you had, say, 5 secondary invariants, the product of any 2 secondary invariants will obey an equation of this form. So you might square a secondary invariant or take a product of any 2 different secondary invariants. None of those are included in our final space because it would be redundant to do so. So our complete space of operators is given by raising the primary invariance to any non-negative power times 1, or raising the primary invariance to any non-negative power times the secondary invariant S. And the direct sum of those two sets is the complete space of gauge invariant operators. It's natural to interpret the first set as a Fock space built on top of the vacuum, and the second set as a Fock space built on top of some non-trivial state S. And this is in line with the argument that we're going to try to make, that the secondary invariants correspond to non-perturbative states of the theory, whereas these primary invariants correspond to perturbative excitations. Okay, I'm not going to do any more proofs. You've seen how we do our proofs. It's all done in this way. So let's now talk about some generalities. So first of all of the partition functions that we've calculated took this form that I've shown you on this slide. In invariant theory, this is known as the Hironaka decomposition. The denominator are known as primary invariants, and each term in the numerator corresponds to a secondary invariant. So this terminology comes from invariant theory. The ring CND of GLN invariants of Dn by n matrices, which is completely the same as the ring of UN invariants of Dn by n matrices, is denoted CND. And the number of this is our ring, this is what we're studying. And the number of primary invariants for this ring has been computed by mathematicians to be d minus 1 times n squared plus 1. So we know how many factors there are in the denominator. The number of secondary invariants is not known in closed form, and the mathematicians are silent on the number of secondary invariants. We will say something about how the number of secondary invariants grows with the rank n of the gauge group. The fact that our partition functions take this Hironaka form is actually key to our analysis. How general is it? Well, this is true for any algebra that is Cohen-Macaulay. So what is a Cohen-Macaulay algebra? Well, an algebra is free when its generators don't obey any constraints. And the Cohen-Macaulay algebras is the nicest generalization of the class of free algebras, which have the same properties that free algebras do. One of those properties is that they admit a Hironaka decomposition. So the question that we're really asking is our ring of invariants Cohen-Macaulay? And the Hochster-Roberts theorem proves that every ring of invariants for a linearly reductive group is Cohen-Macaulay. How do we know when a group is linearly reductive or not? Well, here's a simple test you can do. Take any finite dimensional representation and ask if it's completely reducible. If it is, then you're dealing with a linearly reductive group. So for us, UN, SUN, SON, SPN, they are all linearly reductive. So all of the gauge groups that we like in physics would be covered by the results that we're talking about today. All of them would have a space of gauge invariant operators of the structure that I'm describing. Okay, so here's a comment on primary invariance. So we know that the primary invariance is d minus 1 times n squared plus 1. Something that we do know is that all single trace operators with less than or equal to n matrices inside the trace have to be included as generating invariants. And the reason for that is the trace relations only kick in when you've got n plus 1 matrices in the trace. So you can't express a trace of n or fewer matrices in terms of other invariants. They must be amongst your invariant set. But the question I want to ask is, well, how are they included? Are these single traces included as secondary invariants, or are they included as primary invariants? And to get an idea as to the answer to that question, I'm going to count how many of these single trace invariants there are. Actually, counting the single trace invariance is too difficult, so I'm rather just going to calculate words. I'm going to count how many words there are, so product of L matrices. How many such products of L matrices can I form? Well, each of these matrices can be any of D. So the first could be any one of D, the second, the last could be any one of D. So how many different words are there? It's D to the power of L. This is not the same as counting single trace operators, because, for example, if you look at the trace of x cubed y, they could be any four words. Tracing any four of these words gives you the same single trace operator. But it's not always 4 to 1. Here's another trace of four matrices, and only tracing these two words will give you that single trace operator. And if you look at trace of x to the 4, there's a single word that when you trace it gives you this operator. Why do we get many words for a single trace operator? Well, it's because the single trace operator is invariant under cyclic permutations. But if I do a cyclic permutation and then remove the trace, I get different words. What that shows you is, at most, if you're talking about a trace of L matrices, at most there can be L words that correspond to that single trace operator. So let me do a systematic undercount, and I'll just imagine that I should take d to the L and divide by L to get the number of single trace operators. This systematically undercounts because not every single trace operator corresponds to L words. Some of them will correspond to L over 2 or L over 4 words or something like that. But it turns out that when L is reasonably large, this becomes a very accurate approximation. And you can see that this grows exponentially with L, and the correction due to cyclicity is just a minus log L. So this correction due to cyclicity is a subleading effect. This is a very good approximation. What it does show us is that if we wanted to count the number of single trace operators of length n or more, that will grow exponentially with n. Only n squared of these can be primary invariants, so it turns out that most of these single trace operators have to be included as secondary invariants. Just to give you an idea as to the numbers, let's look at a two-matrix model at n is equal to 20. The total number of single trace operators, so I counted that using polar counting, is 111,321, and only 401 of them are primary. So less than 0.5% of the single trace operators are primaries. More than 99.5% are included as secondaries. I'm going to have to come back to this point and address it, and I will address it a bit later. Okay, so we've talked about the number of primary invariants. What about the number of secondary invariants? So mathematicians don't have a formula, so what we did as a first step, let's look at a two-matrix model, and let's just evaluate that Moline-Weil partition function formula, and let's see what we get. So we had two matrices, we went from 2 to 7. 1 plus d minus 1 times n squared is just 1 plus n squared. That's how many primary invariants we should have. And when we calculated the n is equal to 2 partition function, there were 5 factors in the denominator. When we calculated the n is equal to 7 partition function, there were 50 factors in the denominator. So this nicely matched the number of primary invariants that we should have found. So we grow very modestly from 5 up to 50. Now look at the growth of secondary invariants. We go from 1 to 2 to 64 to 15,000 to 312 million to 21,000 billion. So this growth in the number of secondary invariants is incredibly rapid, much more rapid than a power. And if you just try to fit a power to this growth, what sort of a power do you get? Well, something like e to the n squared fits it best. So to actually prove that this is the growth, we were able to prove that. What we did was we went back to the oscillator and we solved for the exact eigenfunctions. So eigenfunctions of the matrix oscillator can be written as restricted Schur polynomials. Their form is not too important. We wrote them like this. What is important is the following. If you've got a restricted Schur polynomial built with n1a1 daggers and m2a2 daggers, we know the following. The energy is n plus m. R is a Young diagram with n plus m boxes. Little r is a Young diagram with n boxes. Little s is a Young diagram with m boxes. And alpha and beta, these multiplicity labels, run from 1 to the Littlewood-Richardson number RSR. Why is this writing in terms of Littlewood-Richardson number, in terms of restricted Schur polynomials useful? Well, it's useful because in 2019, mathematicians were able to calculate the value of the largest Littlewood-Richardson number. And the largest Littlewood Richardson number, when these young diagrams all have order alpha n squared boxes, is e to the alpha n squared over 2 times the log of 2, and there's an order 1 correction in the exponent. That's how big the correction is. So if we look at the coefficient of x to the alpha n squared inside the partition function, it has to be greater than e to the alpha n squared log 2, because this is the answer that we get by keeping just the biggest term in this sum. So we've managed to lower bound the partition function. We've got a lower bound for the coefficient of x to the alpha n squared in the partition function. Now remember that the partition function is the secondaries at the top divided by the primaries. I've lower bounded the partition function. I can upper bound the contribution coming just from the primaries. If the upper bound from the primaries can't explain the lower bound from the partition function, it means that the secondaries have to supply the difference. And, well, just because of a lack of time, I'm not going to go through these details, but the upper bound for the contribution from the primaries is indeed less than the lower bound of the partition function. What do the secondaries have to supply? Well, the number of secondary invariants has to grow at least as e to an order 1 number times by n squared. So that's the growth of the secondary invariants. It was suggested by our numerical results, but we now have a rigorous proof that the number of secondary invariants must grow as e to an order 1 number times n squared. Well, if you just look at the combinatorics of gauge invariant operators, this growth in the number of secondary operators is only possible if nearly every single secondary invariant is composed using order n squared fields. But this puts us squarely into the regime where we've got operators that are heavy enough that they backreact, so you get new spacetime backgrounds. So this is extremely strong evidence that the secondary invariants do indeed create non-trivial states in our dual holographic theory. If we're looking at quantum mechanics that has black holes in its gravitational dual, we would expect that the typical state of a black hole dominates the ensemble. So if we were to take a look at what's the dimension of this Hilbert space, let's just take the log of the number of secondary invariants, and this gives us c over 1 over n squared, which looks like c over g Newton, which is very reminiscent of a black hole entropy. So we are proposing that these secondary invariants actually correspond to black hole microstates. The number of them fits, and they look like they're heavy. They're operators that are heavy enough that they deform the space-time background. Another thing that's rather interesting is that as n is increased, the character of an invariant can change. So at a given n, you might have an invariant that is a secondary invariant, and as you increase n, this can transition to become a primary invariant, or it might just fall completely out of the set of generating invariants. This looks like a purely bosonic analog of the fortuity mechanism that was recently discovered for 1/16 BPS states. We also expect on general grounds that secondary operators that correspond to solitons must appear in this set. They must appear if the secondary invariants are to describe all non-perturbative states of the theory. These secondaries should have a dimension of order n, so it will be very interesting to confirm whether they appear or not. But now we come back to this puzzle, that the number of single trace operators with less than or equal to n matrices in the trace growed as e to the n. So we've also got lots of secondary invariants that are not heavy. They've got much less than n matrices inside the trace. These light secondary invariants, what is their interpretation? They're not heavy enough to be solitons, and they're certainly not heavy enough to backreact and produce a new space-time geometry. So what do these secondary invariants look like? Well, we've answered this by constructing the list of secondary invariants for specific models. So the small secondary invariants can be decomposed into two types. There are irreducible secondaries. So these correspond to single trace operators with less than n matrices in the trace. But then there's additional secondary invariants that look like they're powers of these irreducible secondaries, and they appear with just raised to some integers. So we're not multiplying secondaries. These single traces to some powers, they appear as the solution to the question, what are the secondary invariants? But what happens is there's a finite number of these, and they appear up to some maximum power n that appears. And if you remember that each single trace operator corresponds to some Kaluza-Klein-Fox space creation operator, the fact that these N1, N2, and Nk have a highest power means that the occupation number of your Kaluza-Klein gravitons have some cutoff. There's a maximum occupation number that you can have. If you put more than that number of Kk gravitons into each state, it turns out you're creating a state that is redundant with some other state that you've got. So the trace relations are pointing out an additional redundancy in gravity, and it means that the occupation number of Kk gravitons is cut off. That implies, and remember, most of these single trace operators landed up amongst these secondaries. So this implies a dramatic reduction in the number of UV degrees of freedom that you would have expected were you just to look in the IR, say it's supergravity or something, and look at the Kaluza-Klein modes that you have. Most of those have occupation numbers that are cut off, and this is implied by the trace relations, so it's a strong gravity effect. So in summary, this is the structure of the space of gauge invariant operators. We have a secondary invariant, so it's a direct sum. Each term of this direct sum is labeled by a secondary invariant. It's addressed by a product of these primary invariants raised to arbitrary powers. The number of primary invariants is d minus 1 n squared plus 1. These are truly perturbative degrees of freedom in the sense that you can raise them to any power and they keep on generating new gauge invariant operators for you. The number of secondary invariant grows as e to the n squared. That means that the vast majority of secondary invariants must be composed of order n squared fields. We've conjectured that the secondary invariants correspond to black hole microstates. As n is increased, the character of invariance changes and secondary invariants transition to become primary, or they might even drop out of the generating set. So we think this is something like a bosonic analog of the fortuity mechanism. It would be fascinating to make that more precise. And finally, the trace relations imply that almost all of the oscillators present in the infrared are cut off as we move to the UV. So the trace relations implement an enormous reduction in the number of degrees of freedom in the UV of quantum gravity. And this will definitely have an important role to play in understanding the UV finiteness of quantum gravity. Thank you for your attention.
Thanks very much, Robert, for this very nice talk. Thank you. Are there any questions?